Hey folks, welcome again to another design programming lecture. This time I want to talk a little bit about artificial intelligence. What does it mean to have a computer that exhibits intelligence, and what have we done throughout history to reach that? So we've got two videos, one on the history of artificial intelligence, what it means and what was covered originally, and then one on where we are today. In 1997, AI got mainstream news coverage for one of the first times in a long time, when this machine, IBM's Deep Blue, beat Garry Kasparov, the reigning chess champion of the world. This is actually one of two machines that were part of Deep Blue. It was a custom hardware build at the time. IBM had built everything from the ground up. And it was able, in its second match against Kasparov, to beat him 4-2 or something or other. A year earlier, he had actually beaten it, which had provided them with the data of exactly what they needed to do to beat him. For a really long time, games of strategy like chess had been regarded as the pinnacle of intelligence. Oh, computers can calculate lots and lots of numbers, but that's not smart. We know that's not smart. Playing a strategy game is smart. Something interesting happened as soon as Deep Blue beat Kasparov. People started saying, chess doesn't require real intelligence either. It just looked ahead a lot, or it just whatever. It just knew, it had played a whole bunch of games in the past. It just knew how this was going, or it was really the humans whose chess skill had beaten Kasparov. And this is actually an example of a much longer thing that happens with the definition of intelligence. As soon as you can do something in a computer, people say, that's not intelligence, a computer can do it. It's almost by definition, right? So chess doesn't require real intelligence. Well, we have computers now that can do logic, logical reasoning, deductions, etc. And so people go, logic, obviously that's a computer thing. Computers do logic. It's not real intelligence. But before computers could do that, it was regarded as a central capacity that only truly intelligent humans could do. We now have machines that can recognize objects, recognize faces, safely steer self-driving cars. But of course, object recognition doesn't require real intelligence. But if you go back to when machines first started doing logic, that was the argument people used. They can reason with logical symbols. If you tell it what a cube is, it can work on a cube, but it can't recognize a person in space. It has no perception. It has no eyes. It just does the reasoning bit. It doesn't do the sensing bit. That would be real intelligence. Except now, you can get a deep learning neural network on your phone that'll be able to recognize whether something is whatever species of bird or not. Is that real intelligence? Is that artificial intelligence? So if you go back far enough, before the invention of computation, people would have said that the capacity to do calculations quickly was an indicator of intelligence, right? Before we had computers, the capacity to do calculation was something that only intelligent people could do. So obviously it was a marker of intelligence. All of this just tells us that we are a very selfish species. And I think it's best summed up by the amazing Doug Hofstadter's quote, AI is whatever hasn't been done yet. At the end of the day, we think we're magic. And if we can reproduce it in silico, then that's not the spark. That's not the real intelligence. By the way, if you find stuff on this area, on the definition of intelligence, and on the relationship between mathematics and art, and all this kind of really interesting, deep symbolic stuff, Doug Hofstadter's Godel Escher book is something of a traditional rite of passage among young computer scientists. I think that anyone who's interested in logic and reasoning and computers and the capability of AI should have a go at this book. It is an interleaved series of stories and explorations of the meaning of computation. Well worth getting into. It is a little long. It's a bit of a commitment, but you should get into it. Anyway, that was a bit of a digression. While I was researching this, while I was looking around for a good picture of deep blue, I actually saw a comment in an article that was literally saying the thing that I wanted to talk about. Some rando JM said, chess is not a meaningful test of intelligence. A more meaningful, although still limited test, is optical character recognition. Feed a marginal photocopy that a person can read with no trouble at all into any OCR package and you get garbage out. Same if you feed in, but a perfect image of text, but in a highly stylized font. The computing power of the human brain in pattern recognition is enormous. That was from 2005. This ancient history in computer science terms. In 2005, someone genuinely thought that good character recognition was intelligence. I don't have to tell you that we can now do all of those things really trivially easy. You can do them on your phone. Goalposts are always being moved in what intelligence means. But maybe we should go back to the beginning. When people first came up with the idea of artificial intelligence as a sensible field of study rather than just as a dream, what did they mean by intelligence? This is the front page of a research proposal written by some mathematicians and what we would now call computer scientists for a summer research project. They wanted some money, as we academics do. You find someone who has money and you pitch them on it. They say, we propose a 2-month, 10-man study of artificial intelligence in the summer of 1956 at Dartmouth College. They wanted to study how computers can think like people, can computers be programmed automatically, can computers be programmed to do logic, a bunch of very fundamental questions. There's a really amazing quote from this. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. So what they're saying here is that the task is to precisely describe intellect. Because once you can do that, the machine can be made to simulate it. Once we can describe it mathematically, you can tell they're mathematicians, right? This is how mathematicians think about the world. Not harshing any mathematicians out there. Once we can understand something, and to understand something means to write down all of the ways it varies, we can simulate it. This tells you an idea of where the field started from. From those early theoretical discussions gave rise to a number of models about how an intelligent agent, and I use the word agent to mean any computational process that acts on a world. I separate it from robot because a robot is necessarily embedded in the physical world, like it has a body and real world senses, but you can have an intelligent agent acting in software, right? It can sit in your browser and look at things that are happening on your computer. But a necessary definition of an agent is that there's the agent itself that exists separate from whatever environment it's embedded in. And the agent has sensors that draw information in from the world, and then it does some reasoning. So that tells it what the world looks like now, and then it does some reasoning to decide what action to take next. And in this case, in this sort of schematic of a very simple agent, it has some rules, which you can think of as kind of if statements, right? That map from if the world is like this, some condition, onto the action that it should take. And so it looks at the world, it sees if the world maps its set of rules about the things it should do, and if it can match something, it will choose to do that. This is called a simple reflex agent. It's the simplest form of any artificial intelligence. Obviously, you can make this much more complicated following these kinds of schematics. Here's a goal-based agent. So what this does is it observes the world, and then it actually has an internal state that it's maintaining about what's happening in the world. So it doesn't just look at what's out there all the time. Like, you keep a reasonable idea of what's behind you. Like, you sort of know about what's going on in the room, but if you can't see what's behind you, I realize this is a terrible idea. I'm looking at the feedback monitor. I can see exactly what's behind me. But assume I was looking this way and I can't see what's behind me. I still have a model in my head of the state of the world beyond the things that I'm looking at right now. Then you're using that and what you're looking at. You update your model about what the world is. But more than that, you actually have some knowledge about how the world evolves. So in other words, if someone's rolled a ball and you've observed it rolling, you're going to assume, even if you turn your back on it, that it's going to keep rolling because you have knowledge about how things, about physical processes, in that case about the physics and the weight of a ball, etc., which allows you to do some prediction even if you're not actively observing it. These are all things you can get an agent to do. Also, you can do some anticipation. So if you have a model of what your actions are likely to do, like if I kick the ball, you have some idea about what's going to happen, then you can use that to update what you think the world will be like in the future if you do that thing. And then you can have a set of goals about what states you want the world to be in. Like I want the ball to be in the goal of my little robot soccer game. Note how my goal here is to score a literal goal, but your goal could just as easily be to get this email sent, to get this meeting scheduled, to pick up a box. These are all possible goals. So I want to choose an action such that I anticipate the world will be in a state that I think of as good. And I've just been told what good is, right? So you can see that you can break down these idea of agents into different steps of reasoning, world building, expectation, anticipation, goal-directed behavior. And while I'm not going to ask you to program any of these, you can sort of imagine what each of those would look like, right? You have to store some idea about a state, and then you have some thing that lets you store how that state is likely to change, and then you can apply that model to other things. You can start to imagine what that would look like in code, even if only on an intuitive level. And from these sorts of architectures, like 20 or 30 years before I was born, probably 40 years before you were born, maybe 50, I don't know, I don't want to dig into that, that feels wild. People started doing things with these sorts of architectures. And I got a couple of really cool examples here. Who's heard of Eliza? Eliza is the psychotherapist chatbot. So Eliza is basically one of those classic therapists who just reflects whatever you said back at you. Just keeps asking vague questions that are designed to get you to elaborate on the old Rogerian model of psychotherapy that says that getting people to talk about their problems will help them. And to some degree it will. We have better models now, cognitive behavior therapy, etc., but this is a reasonable place to start. This program was written in 1966. Here's the kind of stuff it can do. Eliza will start by saying, "Is something troubling you?" And you'll say, "Oh, men are all alike." Well, what's the connection, do you suppose? They're always bugging us about something or other. Can you think of a specific example? Can you note here that Eliza is not actually really understanding what you're saying, but instead pattern matching to an appropriate response? You said all alike. So it has a rule in there that says, well, if someone says they're all something or other, then you say, what's the connection? The idea being, if someone mentions a general statement or says that a whole bunch of things are related, then you should probe them to elaborate. And then if someone says about something or other, or they're always something or other, then you should say, can you think of a specific example? They're always implies that that's an abstraction. So you can probably ask someone to say something specific. And it goes on and on like that. Showing this program to people in 1966 really convinced them that this machine was intelligent, and it really felt like it helped them with their problems. You can go to the address down the bottom there, and you can actually chat with Eliza now, and you can make your own judgment. But there is a potentially apocryphal story about Weizenbaum showing this program to somebody, and then that person asking him to leave the room so that they could talk with it and have a real conversation. They wanted to have a genuine conversation. Now, history does not record whether that conversation yielded any fruit, but it's fascinating how simple. Now, this is a quite complex program. It does a lot of things, but it's a bunch of if statements, right? At the end of the day, it's a bunch of if statements about if they do this, you should say that. It's amazing how much we want to attribute intelligence to things. We are so alone in the universe that we are desperate to find anyone, anything that might share this intelligence that we so value in ourselves. A couple of years later, this is late 60s, around 1970, Terry Winograd put together a program called scherdlu. And scherdlu operated as if it was a robot in an imaginary world of blocks. And you could say things like, pick up the big red block. You're, again, typing text to it. And you say, pick up a big red block. And so it says, okay, picks up the block. It was then re-rendered a few years later with a simple 3D graphical interface where the colors were actually visible. It's amazing how far computer graphics has come, but that's another story. So you'd say things like, grasp the pyramid. And scherdlu would say, I don't understand which pyramid you mean. Grasp the blue pyramid. Okay. The idea here is that Eliza didn't make any attempt to figure out what you were actually talking about. Scherdlu built on that by trying to make a good faith attempt to resolve all of the ambiguities in our speech. It's a huge area of speech understanding, is what were we actually talking about? It's not as simple as you might seem. If you say grasp the pyramid and there's several pyramids, how does a robot know which one you are talking about? Scherdlu, by the way, just as an aside, scherdlu comes from the second line of the keyboard of linotype machines, which were an invention well before the typewriter that was designed to let people quickly set books. So in other words, you needed to put actual metal letters into a mold that could then be pressed onto actual papers to make the book. And how do you quickly typeset a book? Well, you could use one of these machines to set a whole line of type, hence linotype, all at once. With these, you type on this keyboard, and then it actually pours molten metal into molds behind. These things are wild. This is not the purpose of the lecture. I will move on. No, I won't move on. There's one more thing I have to say. I'm sorry, I'm deep diving on this before we get back to AI. The letters of that keyboard were deliberately set out to follow the probability of letters occurring in the English language. E-T-A-O-I-N, etoin, is the first row. Those are the most common letters. And then the next set of most common letters is S-H-R-D-L-D, scherdlu. This analysis at the bottom was done a long time later on the Google Books corpus, so it doesn't quite line up. But it just shows that people have been looking at statistical distributions over letters and trying to find patterns for a really, really long time, such that the keyboard of this machine from like 1898 or something or other is actually following the same distribution that we can find in the Google Books corpus by looking at which letters show up when. Back on topic though, scherdlu. You can say much more complicated things to it. You can say, find a block which is taller than the one you're holding, and put it into the box. And it can work out what the one you're holding means, but it can also work out what the it in put it in the box means, and which box is the box. All of these things have to be resolved. Those ambiguous referents need to be resolved to a specific object. And that's what Winograd was able to do with scherdlu. By the way, I called him Winograd the first time and Winograd this way. That's because I'm sure I was right at least once. You can say things like, does the shortest thing the tallest pyramid's supports support anything green? Yes, the green pyramid. So this just goes to show that once you have taught a machine the rules of something, it can do arbitrarily complicated versions of that task. You and I probably couldn't figure out that sentence. That's a gnarly sentence, but it does follow the rules of grammar that were embedded in scherdlu, so scherdlu can outperform us in that regard, on that very narrow regard. Because if you say, how many things are on top of green cubes? It goes, wait a second. I'm not sure what you mean by on top of. In the phrase on top of green cubes, do you mean directly on the surface of, or do you mean anywhere on top of? That's an important point, right? Sometimes on top of means just on top of, and sometimes it means anywhere above. This is confusing, very confusing to a 1970 algorithm. All of these are rule-based systems. You can think of a rule-based system, as I said earlier, as an if statement, a complicated set of if statements that are all tested at appropriate times. There's a bit more to it. Imagine you wanted a system that gathered knowledge about why a car wouldn't start. You might use something like this. So we're going to define a rule. Don't worry too much about this precise syntax here. We're going to define a rule, and this rule says if you have the car problem named ignition key status on, and then the car problem engine status won't start. So if you have a car that is in that state, the ignition is on, but the car is not, the engine is not, then you can assert, that is, you can know to be true, that you have the car problem starter faulty. So the problem with the car is that the thing named starter is in the status faulty. So you have to be very precise about what you're saying, but you can capture a lot of these things. Those arrow, by the way, is effectively equivalent to if this top bit, then this bottom bit, right? You can capture a lot of knowledge in these traditional rule-based approaches. It was based on stuff like this, that there was a huge amount of hype about what AI could do. And that led to slightly inflated statements like this one by Herb Simon. We have solved the venerable mind-body problem, and we have explained how a system composed entirely of matter can have the properties of mind. That may have gone slightly too far. Herb Simon, by the way, was one of the most famous researchers into cognitive science and artificial intelligence. Simon was convinced that you could solve a lot of AI problems just by building these kind of rule-based systems. But it didn't turn out to be that easy. It turned out that there were many things you couldn't do with this classic first-generation rule-based system approach. And that's the reason why it's now called good old-fashioned AI, the application of logic, rule-based systems, big tables of if statements. To give you an example of, I think, why there's a bit of a problem with this approach, a philosopher, John Searle, came up with what he called the Chinese room argument. This just tells you that at this time, the idea of understanding Chinese was so foreign to people working on this that it was the natural thing to pick when you wanted to pick a language that nobody understood. I don't think they meant any disrespect to China or the Chinese, but they just meant, let's pick something so foreign that we know nobody reading this will understand what we're talking about. Fast forward 60 years, things look a little different. But let's stick with John Searle's formulation there. Imagine you didn't know Chinese, let's start with that, and you were in a room. And inside this room, you had a slot that people could pass paper in and out, and a magical dictionary. And in that dictionary, you could look up a phrase in Chinese, and it said, okay, if you see this phrase in Chinese, then you should respond with this other phrase in Chinese. And there was every possible phrase that you could ever speak in that book with the appropriate response, with an appropriate response. And so you would see in that magic book, you would see if you see this shape, followed by this shape, followed by this shape, then draw this shape, followed by this other shape. You could then, if someone passed through sentences written in Chinese, statements written in Chinese, you'd look them up in your dictionary and you'd respond using whatever it says, draw this shape on paper. If you were just like practice with the calligraphy a little bit, you could convince a person outside that room that the person in the room spoke Chinese. They might be a little slow to respond sometimes, but maybe they were busy, right? You could convince them. It would appear to an external observer that you understood Chinese. But you don't, right? You don't know a word of Chinese. You don't even know what any of these characters mean. You're just being told, if you see that shape, respond with that shape. This, Searle said, was what our rule-based systems are doing. Our rule-based systems, it doesn't matter how smart they appear to be, they don't know the meaning of any of the symbols they're working with. Scherdlu doesn't know what a blue pyramid is or what blue is. Scherdlu just knows that one's blue and that one's a pyramid. We don't know We have no grounding in reality what these symbols mean. Or rather, we do, the computer doesn't. This led to a problem. When it came time to take these things out of the lab and apply them to real-world contexts, it shouldn't surprise any of you that the real world is really messy. And it turns out all of that ambiguity and all of that complexity is just too much to handle using these if statement style systems. You cannot have a large enough database of rules to capture every possibility, even for a quite narrow domain. And so the dreams of folks like Herb Simon about how we'd captured properties of mind in silico withered. And AI research went through what is called the first AI winter, a period where nobody was really doing AI because it wasn't cool and no one would fund it. It came roaring back, of course, first once in the 90s and then again 10 or 15 years ago with the rise of deep learning. Each time we've established that we can do new things, but then we quickly establish boundaries for what we can't do. It seems that old adage about how AI is whatever's left remains true. People can keep saying, oh, now we can recognize cats in videos on YouTube. That's not really intelligent. We'd need to be able to make pictures of cats in our own videos on YouTube. But computers are getting pretty close to doing that. There are robotic content creators out there on the internet today. More about that in the next video. So there's never really been a solution, by the way, to this problem of symbol grounding. We've just gotten a lot faster. But maybe thinking about properties of mind and embedding these high-level cognitive abstractions in our machines, maybe that's not the only way to think about what AI could be. There's another way. And to that, I think I want to quote the words of Mary Catherine Bateson, an anthropologist. I don't know what she was doing here, maybe planning her costume for the next Star Wars convention. But Bateson wrote, "The tragedy of the cybernetic revolution, which had two sides, the computer science side and the systems theory side, has been the neglect of the systems theory. We chose marketable gadgets in preference to a deeper understanding of the world that we live in." What Bateson is saying is that there were always two pieces to this. There was the computer science side, the cognitive science side. What properties can we imbue in a system? Which parts of our own high-level cognition can we see in silico? But then there's also the study of feedback and of systems and how we can embed technology into those. Instead of thinking about agents existing separate from the world, instead thinking about systems of agents embedded in a world where the boundary is not so clear-cut, because our world is dominated by complex systems. Systems of international trade, systems of nature, systems of evolution, systems of physics, systems of society, systems of culture, systems of technology. We now live in a world where complexity is the norm. And it is something of the height of hubris to say that we could abstract all of that away and just talk about the very high-level properties that govern our own intelligence. It was maybe a sensible place to start, but I think it's not necessarily where we're going to have to end up if we ever want to create truly intelligent machines. But I don't want you to think that there was no application for these traditional rule-based systems, even though they haven't really solved the question of what is intelligence. And you'll note I'm not going to answer the question of what is intelligence. Pre-COVID, it was something that I really loved having a discussion with a class about, just making everybody tell me their answers and then not ever giving you a straight answer because I'm an AI researcher and I don't really know. But rule-based systems are used everywhere. We just don't call them AI anymore. In the design of silicon chips, computer chips, such as the one you're using to watch this, what would have been recognized as AI problem solvers, theorem-proving algorithms, are used at the design stage of the new silicon chips, when they have to lay out where all the different transistors go on that tiny little wafer of silicon. They use formal model checking algorithms to prove that you cannot get the system into a state that it can't get itself out of. And that's done using Boolean logic problems, called Boolean satisfiability problems. I actually don't know that much about them. You can go check them out and then you can tell me. And we use them on huge supercomputers to help us design silicon chips, because the chips are just so complicated that we can't check the work ourselves. We need automated logic. Telescopes. Fascinating problem if you have an international asset in space is who chooses who gets time on it. The Hubble telescope has had since its launch, since 1998 or something or other, don't quote me on that one, I could well be wrong, it has had a automated scheduling program that runs on this kind of traditional logic that is used to satisfy making sure that everybody gets something of a go, that projects that need it at a specific time, like when it's rotating around the world at a particular point and can be pointed at some object, that is a really hard scheduling problem. And it has been solved for the last 20-something years by a machine. Even in the same sort of vein of time scheduling, it's not working. I mean, obviously this is a screenshot, but when I went to our wonderful timetabling system to show you a screenshot of the UCID timetable, it was down. And I thought, what the hell, I'm putting that in the lecture. Even our excellent timetabling system that definitely works and doesn't break uses this traditional AI to work. It uses a constraint solver algorithm that when you enroll in a bunch of classes and everybody else enrolls in a bunch of classes, it tries to assign you to sections so that you don't have any clashes, so you don't have any overlaps. It does its best. It's not perfect. But sometimes there isn't a solution. It doesn't matter how much you search with these kind of logic programs, there literally isn't a solution where no one gets a clash. But all of these would have been recognized as triumphs of artificial intelligence back in the time of Weizenbaum and Herb Simon and Terry Winograd, or Terry Winograd. They now are just these crappy bits of infrastructure that don't even work half the time. They're back-end. They're not intelligent. What is intelligence? I don't know, but a computer can't do it yet.